Hello viewers, I am Sujya, your chemistry teacher, and let's begin with the discussion of questions and answers from the unit Electrochemistry of class 12. Hope that you would have gone through the previous 5 videos which I had posted. I have tried my best to include both simple as also some difficult questions so that you get to understand all the concepts well. So, let's take on the next set of 10 questions from the unit Electrochemistry. Question number 1. The E naught values of 3 elements A, B, and C are given. Which of them would serve to effectively prevent the surface of iron from corrosion, given that the standard reduction electrode potentials of iron element A, B, and C are given? Now let's look at their values. E naught value for Fe2 plus bar Fe minus 0.44 volt. E naught, the reduction potential value for A plus bar A minus 0.74 volt. E naught value for B2 plus bar B minus 0.13 volt. E naught C2 plus bar C minus 0.16 volt. The options are given. Look at the options. First option, element A only. Second option, element B. Third option, both elements B and C. Fourth, element C only. Now, if you look at the standard reduction electrode potential values, all are negative. What does it mean? The negative value of standard reduction electrode potentials indicate that reduction reaction at these electrodes is not spontaneous. Rather, their tendency is to undergo oxidation. Greater the negative value of standard reduction electrode potential, the easier it would be for such an element to undergo oxidation. Greater the negative value of standard reduction potential value, higher would be its tendency to undergo oxidation. So if you look at the standard oxidation electrode potentials of elements A, B, and C, what you have to do is just change the sign of the electrode potential. If it is minus in the reduction potential, it would become positive in the oxidation potential. So oxidation potentials of A, B, and C are plus 0.74, plus 0.13, and plus 0.16 volt respectively. Now, what about the oxidation potential of iron? Plus 0.44 volt. If you look at the oxidation potential values, the value for A is greater than that of iron, which is 0.74 volt. So, this element A would rather get oxidized in comparison to iron when exposed to moist atmosphere. Therefore, element A would serve effectively to prevent the surface of iron from corrosion. Hence, option 1 is the right answer. Question number 2. A current of 2.5 amperes is passed through 500 ml of 0.3 molar solution of copper sulfate for 2 hours with a current efficiency of 90%. Calculate the final molarity of copper sulfate solution assuming the volume to remain constant. This problem is based on Faraday's laws of electrolysis. So let's see the calculations. First, we need to calculate the quantity of electricity passed in coulombs, which is Q. Q is equal to current I passed into time t seconds. But it is given that the current is 2.5 amperes and the current efficiency is 90%. That means only 90% of it is used. Hence, 2.5 into 90 by 100, which is 2.25 amperes. So, 2.25 amperes of current only is passed through the electrolytic cell containing copper sulfate solution. What about time? Time in hours to be converted to seconds. 2 into 60 into 60, that is 7,200 seconds. And substituting the value of current I and time t, we get Q, the quantity of electricity passed in coulombs, which is 2.25 into 7,200, which works out to be 16,200 coulombs. Here I have just converted the coulombs into Faraday. You can use the value as such, but for a change I converted this coulombs into Faraday. We know that 96,500 coulombs is equal to 1 Faraday. Therefore, 16,200 coulombs would be equal to 16,200 divided by 96,500 into the whole thing into 1, which is 0.1679 Faraday. Now coming to the reduction reaction occurring in the electrolytic cell, it is cupric ions Cu2 plus taking up 2 electrons and getting reduced to copper metal. So copper ions are getting used up during the electrolytic cell. How? They are getting reduced to metallic copper. Now, from the equation reduction reaction, it is seen that 2 Faradays of electric current is required to convert 1 mole of copper ions to copper. How 2 Faradays? Because 2 into 96,500 coulombs. I kept this problem for a change. I wanted to work it out in terms of Faradays of charge. So 2 Faradays of electric charge is required to convert 1 mole of copper ions to copper metal. So 0.1679 Faradays of current will convert how much of copper ions to copper? It would be 0.1679 into 1 mole divided by 2. 2 Faradays, that 2. So it is equal to 0.084 moles of copper ions have got converted to copper metal. It is mentioned in the problem that initial molarity is 0.3 m, which means that 0.3 moles of copper sulfate are present in 1 liter of the solution. Therefore, the initial number of moles of copper ions in 500 ml would be 0.3 into 500 by 1000 or 0.3 into 0.5, which is 0.15 moles. Therefore, the initial number of moles is 0.15. The number of moles of copper ions which have disappeared from the electrolyte. Why? Because they have been converted to copper metal is 0.084 moles. Therefore, the number of moles of copper ions left in the solution would be 0.15 minus 0.084 moles. When you subtract, you get it as 0.066 moles. So, therefore, the final molarity of the solution, 0.066 moles are present in 500 ml. Therefore, whenever we talk about molarity, it is the number of moles in 1 liter of the solution. So, the molarity of the solution would be 0.066 into 1000 by 500, which is 0.132 mole. So the molarity of the solution which is remaining is 0.132 mole. Question number 3. Given below are 4 statements. Choose the correct statement. A. When silver electrode with a standard reduction electrode potential equal to plus 0.8 volt is coupled with She is standard hydrogen electrode. It will act as anode while she will act as cathode. B. Tin coating on iron articles acts as sacrificial anode and protects iron from corrosion. C. The cell potential of mercury cell remains constant throughout its life. D. The change in free energy delta G is less than 0 for an electrolytic cell while delta G is greater than 0 for a galvanic cell. Now, if you look at these 4 statements, the first statement deals with construction of a galvanic cell with silver electrode and standard hydrogen electrode. The second, tin coating, it deals with protection of iron from rusting by tinning. Statement C deals with mercury cell, which is a secondary cell, and D statement deals with free energy changes taking place in electrolytic cell and in a galvanic cell. Statements A, B, and D are wrong statements. They are incorrect. The corrected statements I have given here. That is, when silver electrode with a standard reduction electrode potential value equal to plus 0.8 volt is coupled with it will act as cathode while she will act as anode. We know that the reduction potential of SHE is fixed to be equal to 0.0 volt. So when compared to the silver electrode with a higher value of reduction potential, that is plus 0.8 volt, will act as cathode. Silver electrode would serve as cathode while she would function as anode. That's the corrected statement. That is based on the reduction potential values. The greater the positive value of reduction potential, the higher is its tendency to undergo reduction. Silver electrode shows greater tendency to undergo reduction. Therefore, it would function as cathode in this galvanic cell. B statement. Tin coating on iron articles will not act as sacrificial anode. Why? Because the standard reduction electrode potential value of tin, which is E0 SN2 plus bar SN, is minus 0.16 volt, which is higher than that of the iron, the standard reduction potential of iron, which is Fe2 plus bar Fe, which in other words, what I mean to say is the more negative reduction potential value is that of iron, that is Fe2 plus bar Fe. So greater the negative value of the standard reduction potential, higher would be its tendency to get oxidized. Hence, iron articles would undergo oxidation more readily and form rust if and when the tin coating on their surface gets damaged and exposes iron surface to moist air. In the presence of tin, iron would undergo corrosion faster. So there is no point in stating that tin metal acts as sacrificial anode. Sacrificial anodes will have, uh, if you look, larger negative value like that of Mg2 plus. Only then they can act as an sacrificial anode. Statement D. We know that in electrolytic cells, energy has to be supplied, electrical energy has to be supplied in order to carry out the redox reaction. In electrolytic cells, therefore, delta G would be greater than 0. But in galvanic cells, where as a result of chemical reactions taking place, electrical work is done. In such galvanic cells, delta G would be less than 0. So, galvanic cells, delta G is less than 0. Electrolytic cells, delta G is greater than 0. Statement C is the correct statement. The cell potential of mercury cell remains constant throughout its life because the overall cell reaction does not involve any ions whose concentration changes during its lifetime. In the next slide, I have shown the mercury cell. If you look at the mercury cell, it's a secondary cell. It is in the form of a small steel button. It is used in wristwatches and other such electronic devices. The anode comprises of zinc mercury amalgam, ZnHg amalgam, while the cathode is made of a paste of mercuric oxide, that is solid mercuric oxide, and graphite powder. So if you look at the overall cell reaction, zinc amalgam, ZnHg plus mercuric oxide solid gives ZnO, zinc oxide solid plus mercury metal. This cell reaction, you see there are no ions involved in the reaction. No ions participate in the cell reaction. So therefore, there is no chance of the cell potential of mercury cell to change during its lifetime. In other words, the cell potential of mercury cell would remain a constant throughout its life. Question number 4. A metallic plate with surface area of 800 square centimeter is electroplated with gold Au by passing a current of 6 amperes for 4 hours through auric chloride solution, AuCl3 solution. What would be the thickness of gold metal deposited on the plate? Given density of Au is 19.3 gram per cc and atomic mass of Au is 197 gram per mole. Yet again, we see that this problem is an application of Faraday's laws of electrolysis, but with a slight twist to it, because after getting the mass of gold deposited, we need to find the thickness of the metal which is deposited on the plate. So let's get started with solving the problem. The required equation is Au3 plus auric ions plus 3 electrons gives Au solid, gold metal deposited. Quantity of electricity Q is equal to I into T. Q is in coulombs. Q coulombs is equal to current I in amperes into time T in seconds. Converting 4 hours into seconds, 4 into 60 into 60. We get therefore Q is equal to 6 into 4 into 60 into 60, which is 86,400 coulombs. From the given equation, that is the reduction reaction of auric ions to gold metal, we see that 96,500 into 3 coulombs of charge deposits 197 grams of gold metal. The atomic mass of gold is 197 gram per mole. So 96,500 into 3 coulombs of charge will deposit 1 mole of gold metal, which is 197 gram of gold metal. So therefore 86,400 coulombs will deposit how much of gold? That is 86,400 into 197 divided by 96,500 into 3, which is 58.79 gram of gold metal gets deposited. Now we need to find the thickness. Suppose the thickness of gold metal which gets deposited is y centimeter, and given in the problem that area is 800 square centimeter, as also density of gold is 19.3 gram per cc. Therefore we know that mass is equal to volume into density, and volume is area into thickness. Therefore mass works out to be area 800 into thickness, which we have taken as y, into density 19.3. Substituting the mass which we got as 58.79 gram. So therefore 58.79 gram is equal to 800 into y into 19.3. Therefore y is equal to 58.79 divided by 800 into 19.3, that is equal to 0.0038 centimeter. That is the thickness of gold metal which gets deposited on the metallic plate. Question number 5. When a specified quantity of electric current was simultaneously passed through aqueous solutions of silver nitrate AgNO3 and a soluble salt solution of platinum kept in two separate containers, the masses of silver and platinum deposited at their respective cathodes were 0.896 gram and 0.404 gram respectively. Calculate the oxidation state of platinum in the compound. Atomic mass of silver is given as 108 mu, which is grams per mole, and platinum 195 mu, 195 grams per mole. This problem is an application of Faraday's second law of electrolysis. Faraday's second law of electrolysis states that when the same quantity of electricity is passed through different electrolyte solutions connected in series, the masses of the substances produced at the electrodes are directly proportional to their chemical equivalent weights. That's Faraday's second law of electrolysis. You have to be thorough with Faraday's first and second law of electrolysis. Now, calculation. First, to calculate the charge in coulombs passed through the two electrolyte solutions, take silver nitrate first. Ag plus ions will accept an electron, get reduced to metallic silver. 96, only 1 mole of electrons are involved in the reaction. So, 96,500 into 1 coulomb of charge deposits 1 mole of silver metal or 108 grams of silver. So, how much of charge will deposit 0.896 gram of silver? So that is 96,500 into 0.896 divided by 108, which is 800.59 coulombs. So that much of charge would be required to deposit 0.896 gram of silver metal. Coming to the reduction of platinum, we don't know the oxidation state of platinum. Let it be taken as N. Always we take X, here I put it as N. So PTN plus requires N moles of electrons to get reduced to platinum metal. So from this reduction reaction, we can write the equation as 96,500 into N coulombs of charge will deposit the atomic mass of platinum, which is 195 gram of platinum, which is 1 mole of platinum. So 96,500 into N coulombs of electrical charge deposits 195 grams of platinum. So how much of charge is needed to deposit 0.404 gram of platinum as asked in the problem? So that is 0.404 into 96,500 into N divided by 96,000 divided by 195. So much of coulombs of charge is required. Now, applying Faraday's second law, since the quantity of charge flowing through the two electrolyte cells is the same, so equating it, we got the quantity of charge in the first case as 800.59 coulombs, and in the second case it is 0.404 into 96,500 into N divided by 195 divided by 195. So we get, equating the two, we get, because the quantity of charge flowing through the two electrolyte solutions is the same, therefore we can equate the two. We get 800.59 coulombs is equal to 0.404 into N into 96,500 divided by 195. Therefore, N is equal to 800.59 into 195 divided by 96,500 into 0.404, which is equal to 4.004. Within limits of experimental error, this is approximately equal to 4. So, what is N here? N is the oxidation state of platinum. We have represented it as PTN plus, isn't it? So, this N is equal to 4. Therefore, we can say that the oxidation state of platinum is 4, PT4 plus. Question number 6. What is meant by electrochemical equivalent of a substance? It's abbreviated as ECE. The answer is electrochemical equivalent of a substance is the mass of a substance in grams that is either deposited or consumed on one of the electrodes when a current of 1 ampere is passed for 1 second through the electrolytic cell. We know that 1 ampere into 1 second is 1 coulomb. So, the definition can be altered as electrochemical equivalent of a substance is the mass of a substance in grams that is either deposited or consumed on one of the electrodes when a current of 1 coulomb is passed through the electrolytic cell. 1 coulomb is passed through the electrolytic cell. So both definitions are accepted as electrochemical equivalent of a substance. Mathematically, M is equal to Z into I into T. Here Z is the symbol for electrochemical equivalent of a substance and I current in amperes time t in seconds, that is I is 1 ampere time t is 1 second. Unit of Z is gram per coulomb. What are the characteristic features of Z? Different substances have different electrochemical equivalents. Why? What is the reason? Because the atoms or ions which are deposited on either of the electrodes have different atomic masses. Therefore, Z value depends on the nature of atoms or ions that get deposited on the electrodes. Second factor, different charge carried by the ions. The Z value also depends upon the charge carried by the atoms or ions. So that's about characteristic features of Z. Now, example, I've taken two examples. First one is for getting silver metal deposited. We know that silver ions require only 1 mole of silver ions. 1 mole of silver ions require only 1 mole of electrons to get deposited as 1 mole of silver metal. Therefore, 96,500 coulombs of charge deposit 1 mole of silver or its atomic mass 108 grams of silver. Therefore, 1 coulomb of charge will deposit how much of silver? 1.0 coulombs into 108 divided by 96,500 coulombs. That is equal to 0.00119 gram per coulomb. Another example taken is that of copper ions. 1 mole of copper ions require 2 moles of electrons to get reduced to copper metal. Therefore, we can say 2 into 96,500 coulombs of charge is needed to deposit 63.5 grams of copper metal. So, 1 coulomb of charge will produce how much of copper metal? 1 into 63.5 divided by 2 into 96,500, which is equal to 0.000329 gram per coulomb, which is the electrochemical equivalent of copper. So see how we can easily calculate the electrochemical equivalent of any substance. Coming to question number 7, that also deals with, is related to electrochemical equivalent of a substance. Here the problem is, if the electrochemical equivalent of a metal X is 9.36 into 10 power minus 8 kilogram per coulomb. Just see that mass is given in kilogram, but always we have to report the mass in grams. So 9.36 into 10 power 8 kilogram we must be converted into grams. We'll keep that in mind. Once again, the problem. If the electrochemical equivalent of a metal X is 9.36 into 10 power minus 8 kilogram per coulomb, what is the charge carried by it? So, atomic mass of the X metal element is given as 27 grams per mole. So, we have to calculate the charge carried by this element X. Let us write the reduction reaction as X raised to the power n plus n moles of electrons gives X solid. So, from this equation, we can say that n moles of electrons are required to reduce 1 mole of Xn plus, that is Xn plus charge to X metal. Therefore, 96,500 into n coulombs of charge deposits 1 mole of the metal. 1 mole of the metal is atomic mass of the metal given in the problem as 27 gram per mole. Therefore, 96,500 into n coulombs of charge deposit 27 grams of metal X. So, 1 coulomb of charge will deposit how much of the metal? That would be equal to 27 into 1 divided by 96,500 into N. This will be the electrochemical equivalent Z of the metal which is getting deposited. But the Z value is given in the question, 9.36 into 10 power minus 8 kilogram per coulomb. To convert kilogram into gram, multiplied by 1000. 9.36 into 10 power 3 into 10 power minus 8. That will become 9.36 into 10 power minus 5. 10 power 3, 10 power minus 8 works out to be 10 power minus 5. Therefore, we get 27 into 1 by 96,500 into n is equal to 9.36 into 10 power minus 5. Therefore, n would be 27 divided by 9.36 into 10 power minus 5 into 96,500, which is equal to 2.89 into 10 power minus 5 into 10 power plus 5. 2.989 into 10 power minus 5 into 10 power plus 5, which is nearly equal to 3. This is within limits of experimental error. 2.989 is nearly equal to 3. So, what is 3? N, the charge carried by X. Therefore, the charge on the metal X is plus 3. It can be represented as X plus 3. Question number 8. The cell reaction occurring in a galvanic cell is 3 Fe2 plus aqueous plus 2 Cr solid gives 3 Fe solid plus 2 Cr3 plus. Molar concentration of Cr3 plus is 0.2 molar and Fe2 plus molar concentration is 0.4 molar. Calculate the cell potential. Application of Nernst equation. And E naught electrode value of Fe2 plus bar Fe is given minus 0.45 volt, and E naught electrode potential of Cr3 plus bar Cr is also given minus 0.75 volt. So, to arrive at the cell potential, we need to do the calculation in 3 steps. In first step, we calculate E naught cell. Given the E naught value of of ferrous bar Fe and Cr3 plus bar Cr. So for that, if you look at the overall redox reaction, in this Fe2 plus is getting reduced to Fe and chromium Cr is getting oxidized. So the chromium electrode would act as anode while Fe2 plus bar Fe will act as cathode. This is from the redox reaction occurring and also from the E naught electrode potential values. So E naught cell is equal to E naught cathode minus E naught anode, which is minus 0.45 minus 0.75, which is equal to plus 0.30 volt. Second step, we need to find the N value, the number of electrons involved in the redox reaction. If you look at the reaction at the anode, if we look at the reaction taking place at the anode, it is chromium losing 3 electrons to give Cr3 plus. And at the cathode, reduction occurring is Fe2 plus accepts 2 electrons to form Fe solid. Equation 1 and 2, you see the number of electrons given out by chromium is not the same as the number of electrons accepted by Fe2 plus. Hence, to equalize the number of electrons given out and taken up, we need to multiply equation 1 into 2 and equation 2 into 3. So we get 2 Cr minus 6 electrons give 2 Cr3 plus, and 3 Fe2 plus 6 electrons gives 3 Fe solid. Therefore, the number of electrons released by chromium is the same as the number of electrons accepted by Fe2 plus, which is 6 electrons. Now, third step. Using Nernst equation, we can calculate the cell potential. E cell is equal to E naught cell minus 0.059 by N log molar concentration of chromium ions, the whole square, divided by molar concentration of Fe2 plus, the whole cubed. Substituting the values, we get E cell is equal to plus 0.3 volt, E, which is E naught cell value, minus 0.059 by 6 log of molar concentration of Cr3 plus is 0.2. 0.2 the whole square divided by 0.4 the whole cubed. So it is plus 0.3 minus 0.059 by 6 log of 0.2 the whole square divided by 0.4 the whole cube, which is equal to plus 0.3 minus 0.059 by 6 into, when we solve the log quantity, we get 0.7957. After multiplication, we get, that is 0.059 by 6 into 0.7957, we get it as 0.00782. Therefore, E cell is equal to plus 0.3 minus of 0.00782, which is equal to plus 0.2922 volts. So 0.2922 volts is the potential of the cell potential of the given cell. Cell potential of the given cell. Ninth question. If the standard reduction electrode potential of platinum Pt, Cl2 bar 2Cl minus chloride ions 2Cl minus is plus 1.36 volt, what would be the reduction electrode potential of an electrode at 298 Kelvin, which is shown as given below? Pt, Cl2, platinum with chlorine gas absorbed on it. Partial pressure of chlorine gas is 2 atmospheres. Dipping into HCl solution, concentration is 0.02 molar. A look at this electrode shows that this electrode is not functioning under standard conditions because the partial pressure of chlorine is not 1 atmosphere, but it is given as 2 atmospheres. The molar concentration of HCl is not 1 molar, but 0.02 molar. Therefore, this electrode is not functioning under standard conditions. We need to find out the E electrode value of this electrode. Now, this is a gas electrode which is called as chlorine electrode, and at this chlorine electrode, the reduction reaction occurring can be represented as Cl2 plus 2 electrons give 2Cl minus aqueous. A look at this reduction reaction shows that N value is equal to 2. Now, the general equation for The general Nernst equation for an electrode is given as E electrode is equal to E naught electrode minus 0.059 by N log of reduced product divided by oxidized product. Log of reduced product by oxidized product. So, applying this general Nernst equation to our given electrode, we get E Cl2 bar 2Cl minus is equal to E naught Cl2 bar 2Cl minus 0.059 by 2 log of molar concentration of Cl minus the whole square divided by the oxidized product is chlorine gas. So here partial pressure, the concentration is in terms of partial pressure. So reduced product is Cl minus the whole square divided by oxidized product partial pressure of chlorine. It is given that partial pressure of chlorine is 2 atmospheres and molar concentration of Cl minus is 0.02 molar. Substituting the values in the equation, we get E electrode is equal to plus 1.36 minus 0.059 by 2 log of 0.02 the whole square divided by 2 log of 0.02 the whole square divided by 2. So taking logs and subtracting, we get plus 1.36 minus 0.059 by 2 into minus of 4.6020 minus 0.3010. On calculation, we get E Cl2 bar 2Cl minus is equal to plus 1.36 plus 0.0295. Not 295, how did I get? By dividing 0.059 by 2. So plus 0.0295 into 4.9030. There are two negative signs that has been now converted to positive sign. So the E electrode is equal to plus 1.36 plus 0.1446, which is 1.5046 volt. So the electrode potential of the chlorine electrode works out to be 1.5046 volt. Here, with the only caution to be taken is using Nernst equation, where log values are reduced log of reduced product by oxidized product. I have also shown a galvanic cell where chlorine electrode functions as the cathode. 10th question. For the given electrode reaction Cr2O72 minus plus 14H plus 6 electrons gives 2Cr3 plus 7H2O. The following data is given. E0 electrode value is plus 1.33 volt. E electrode value is plus 1.067 volt. Molar concentration of Cr3 plus is 1.5 into 10 power minus 2 moles per liter, and that of dichromate ion Cr2O72 minus is 4.5 into 10 power minus 2 m. Calculate the pH of the solution. Options are given. We need to choose the right option. If you look at the cell reaction, here the dichromate anion Cr2O72 minus in acid medium, that is 14H plus, is reduced to Cr3 plus along with formation of water. So the given electrode reaction is Cr2O72 minus plus 14H plus 6 electrons gives 2Cr3 plus 7H2O. So this electrode is the dichromate electrode. E electrode, we can use Nernst equation for an electrode and write it as E electrode is equal to E naught electrode minus 0.059 by N log of reduced product by oxidized product. So here the reduced product is chromium ions, molar concentration of chromium ions, because two chromium ions are formed. So Cr3 plus the whole square divided by oxidized product, molar concentration of Cr2O7 dichromate into that of H plus ions, into H plus ions. And how many H plus ions are involved? 14 H plus ions. So we can write the equation by substituting the values. 1.067 E electrode is equal to E naught electrode 1.33 minus 0.059 by 6, n is equal to 6 here, log of 1.5 into 10 power minus 2 the whole square, that is molar concentration of Cr3 plus, divided by molar concentration of dichromate, which is 4.5 into 10 power minus 2 into molar concentration of H plus ions raised to the power 14. That is equal to 1.067 is equal to 1.33 minus divide 0.059 by 6, we get 0.00983 into log of 50 into 10 power minus 3 divided by H plus ion concentration raised to power 14. So in this case, bringing 1.33 to the other side, we get minus 0.00983 log of 50 into 10 power minus 3 divided by H plus ions raised to power 14 is equal to minus 0.263 volt. So log 50 into 10 power minus 3 divided by H plus ions is equal to minus 0.263 divided by minus 0.00983. After dividing minus 263 by 0.00983, minus and minus gets cancelled, we get 26.755. Therefore, log 50 into 10 power minus 3 minus log H plus ion concentration to the power 14 is 26.755. Now, minus 14 log H plus is equal to 26.755 plus 1.301. How did we get 1.301? That is log 50. Log 50 into 10 power minus 3. We have got it as minus 1.301, which when it is brought to the other side, it becomes plus. So we get minus 14 log H plus concentration is equal to 28.056, or minus 14 log H plus ion concentration is equal to plus 28.056, bringing 14 to the other side we get, or minus log H plus ion concentration is equal to plus 28.056 divided by 14, which is 2.004. We know that negative log to the base 10 of hydrogen ion concentration is pH of the solution. Therefore, pH is equal to 2.004. Hence, option D is the right answer. In the last portion of this video, I have included some important relationships between delta G naught, E naught cell and Kc, the equilibrium constant. And also the differences between an electrochemical cell, that is a galvanic cell, and electrolytic cell. So first, delta G naught, we know that is equal to minus NF E naught cell. But E naught cell is 2.303 RT log Kc by NF. That is the E naught cell value. Substituting the E naught cell in delta G naught equation, we get delta G naught is equal to minus NF into 2.303 RT log Kc, the whole divided by NF. NF and NF get cancelled. Therefore, delta G naught is equal to minus 2.303 RT log Kc, where R is the ideal gas constant whose value is 8.314 joules per Kelvin per mole, and T temperature is 298 Kelvin, 25 degrees Celsius. Then, one thing we should remember is that E naught cell is an intensive property. That property, that is the intensive property, does not depend upon the amount of matter present in a sample. Such examples, E naught cell is one example. The other examples are concentration, molar concentration, temperature, pressure, density, boiling point. These are certain properties which are labeled as intensive properties. The other one, extensive properties. Delta G naught is an extensive property, or Gibbs free energy, in other words, is an extensive property, meaning that it is dependent on the amount of matter present in a sample. Examples are volume, mass, and such thermodynamic state functions like Gibbs free energy, entropy, enthalpy, internal energy, etc. So one should know to differentiate between intensive and extensive property. Hence, E naught cell is an intensive property, while G naught, the Gibbs free energy state change in the standard state, is an extensive property. Now, coming to difference between galvanic cell or electrochemical cell and electrolytic cell. 1. Galvanic cell is a gadget, a device which converts chemical energy into electrical energy. As a result of redox reactions, electrical energy is produced. Electrolytic cell, it's a device which converts electrical energy into chemical energy. By passing electric current, you bring about a chemical change. Second, redox reaction is spontaneous in a galvanic cell, and that is responsible for production of electrical energy. In electrolytic cell, redox reaction is not spontaneous, and electrical energy is supplied to carry out the redox reaction. 3. In galvanic cell, anode functions as the negative electrode and cathode acts as the positive electrode. But in electrolytic cell, anode is assigned positive polarity. Anode is the positive electrode while cathode serves as the negative electrode. Fourth difference, the electrons move from anode to cathode in the electrical circuit, where in a galvanic cell, whereas in an electrolytic cell, the electron supplied by the battery enters through the cathode and comes out through the anode. So these are four important differences between a galvanic and electrolytic cell. You can answer any question based on this concept. So we have finished 10 questions in part 2 electrochemistry unit. Part 3 of it will be put in days to come. That's why I've written as to be continued, in which I will include questions where calculation of equilibrium constant and more problems on molar conductivity, resistance of a cell, etc. will be dealt with. So thank you.